In my last video, I have explained spectrophotometric calculations. In this class, I am going to explain single component analysis and multi-component analysis. Okay, let's see one by one. Single component analysis. The name itself indicating here the solution consists single component, only one component. Other name is one component analysis. Okay, if the solution consists single component, okay, that concentration is determined by following. Okay, these ways. Here, first one, the absorbance of standard and unknown are compared with lambda max of compound in particular solvent. First, the absorbance of standard, okay, that is denoted as AS, and then absorbance of unknown, denoted as AU. U means unknown, S means standard, are compared with lambda max. Okay, I compared with lambda max of the compound in particular solvent. Here we know that here every compound having own lambda max. Here this time we are comparing our unknown sample with the standard sample at the lambda max in particular solvent. We know that in particular solvent, okay, here same compound will show same absorbance. Okay, same compound will show same lambda max. That we know that. Okay, the absorbance of standard AS and the absorbance of unknown are compared at lambda max of compound in particular solvent. Okay, the contents of unknown calculated by the following formula. After comparing, here the contents of unknown AU, that is calculated by following formula. This formula CE equal AU by AS into CS. Here the C denotes concentration of unknown. C means concentration, U means unknown, A means absorbance, U means unknown, absorbance of unknown, divided by A means absorbance, S means standard, absorbance of standard, into C means concentration, S means standard, like this. Okay, C means concentration, U means unknown, S means standard, U means unknown, A means absorbance. By using this formula, we can determine the concentration of unknown sample with the comparing of standard sample. Okay, or we can also use another formula. Not only this, we can also use another formula, that is Beers-Lambert's law equation. We know that Beers-Lambert's law equation, that is A equal epsilon BC, or A equal ABC, small a BC. Here it can be epsilon, it is replaced with small a, that also we know that. Here epsilon is molar extinction coefficient or molar absorptivity, or simply known as absorptivity. Okay, we know that A means absorbance. Here I given that A means absorbance. Here epsilon or A means molar extinction coefficient or absorptivity, and B means path length. We know that here cuvette length. Path length generally it will be constant, that is 1 centimeter, and C means concentration. Here in that what we need to determine, see, concentration we need to determine, right? So then it will be A by epsilon B. Okay, A by epsilon B. Here we know that B is the constant. If you know the absorbance value, and if you know the molar extension coefficient and absorptivity value, then concentration of the unknown compound will be determined. Okay, determined. Then second way is standard calibration curve is plotted. Standard calibration curve is plotted. Here we know the calibration curve that is plotted between concentration versus absorbance. Okay, using series of standard solution of different concentration. Using series of standard solution of different concentration versus absorbance. Okay, then concentration of unknown sample is determined from the graph. So standard calibration curve is plotted by with here we need to prepare series of standard solution, series of various concentrations of standard solution, like 2, 4, 6, 8, 10 microgram per ml of standard solution concentration we have to prepare, and for that concentration we have to observe absorbance, and any one of the concentration that sample concentration means either maybe 2 microgram per ml or 4 microgram per ml or 6 microgram per ml or 8 or 10, like that. Any one of the concentration you have to prepare. Then for that then the concentration can be determined from the graph. This is about single component analysis. Then multiple or multi-component analysis means if this time the sample consists not only one compound, more than one compound. How we will determine? The concentration of those compounds? You can see if the sample solution consists more than one component, by using absorption measurements, okay, the concentration of individual component in mixture can be determined. without a separation. Okay, once you observe it, if the sample solution consists more than one component, more than one means at least it should have two components. Okay, by using the absorption measurement, the concentration of individual components present in the mixture, can be determined without separation, without needing of separation. How? Here we have several methods. Multi-component analysis can be done by any one of the following method. Here I have given some list of the multi-component analysis. Okay, analysis method. First one, important one, simultaneous equation method. And derivative spectrophotometry, second method. Third method is absorption correction method. Fourth method is geometric correction method. Fifth method is absorbance ratio method. Sixth method is orthogonal polynomial functional method. And seventh method is dual wavelength method. Eighth method is area under the curve. And ninth method is least square extraction method. Here these nine methods have been used for the determination if the solution consists more than one component. Any one of the method you have to use. Okay, in this class I am going to explain only one method, that is simultaneous equation method. That is very, very important for generally this method is commonly used for estimation for multiple component in a solution. Okay, I am going to explain only simultaneous equation method. Let's see. Here I have given explanation about simultaneous equation method. Okay, here for if the concentration of multiple compound determined by simultaneous equation method, we need certain conditions. Certain conditions are applied to this method. What are those? Here this method is simply it is known as SCM. Okay, here conditions, what are those required? First one, if the sample consists two absorbing components, at least it should consist two absorbing components. What are those? Here for example I consider those are one component is X, one component is Y, and each of which should have some absorbent at lambda max at other. Each of which should have some absorbance at lambda max at other. Then only here simultaneous equation method will be applicable. Then only the concentration can be determined. Means, okay, here at least it should consist two observing species. Means two components should be there. Those can be considered as X and Y. Each of which should have some observance at lambda max. Means X is having one lambda max and Y is having one lambda max, because those two are two different components. So it possesses two different lambda max. And what it's saying here, at each lambda max, both the compounds showing some absorbance. Means nothing but here X component having one lambda max. Okay, suppose X component having 270 nanometer. Y component having 285 nanometer, like that. If X lambda max is 270, Y lambda max is 285 nanometer, means here X component should show somewhat absorbance of Y lambda max, at least. Here at least it has to show somewhat absorbance at Y. Here Y components, it has to show somewhat absorbance at X lambda max. That is the meaning here. Okay. Then second condition, the absorption spectra of lambda max of two components reasonably different or dissimilar. Okay, the lambda max of two components reasonably should be dissimilar, not similar. Okay, and there should no chemical interaction between the components. Here solution consists two components. These two components should not interact chemically. Okay, should not interact chemically. Then they must obey Bayes' law. These four conditions are required. Four conditions are applied for simultaneous equation method. Then some more requirements are necessary. What are those? Okay, requirements. The absorptivities of X at lambda 1 is AX1 and lambda 2 is AX2. I told you that X should be shown here. Suppose X is having a lambda max Y1. You consider lambda 1 is a lambda max of the X1. X. Okay, it should show somewhat absorptivity at the Y component, Y lambda max. Okay, the absorptivity of x at lambda 1, that is known as ax1. The absorptivity of x at second wavelength, that is by lambda 2, that is ax2. And the first wavelength is considered as ax1. The second wavelength is considered as ax2. Here same, the absorptivity. You need to understand absorptivity, not the absorption. The absorptivities of y at lambda 1 means first wavelength is a by 1 and second wavelength is a by 2. Okay, same similarly. Okay, at first wavelength is considered as a by 1 and second wavelength is considered as a by 2. Then these two are absorptivities of x and y at both the wavelengths. Okay, ax1, ax2, a by 1, a by 2. Then the absorption of dilute sample. The absorption of dilute sample, that is a mixture. Okay, at lambda 1 is known as a1 and lambda 2 is known as a2. A1 means absorbance and A2 is absorbance. Absorbance as first wavelength, absorbance as second wavelength. Means you see here this x and y means these two are separately we have to perform standard solution. Separately we have to check the absorbance of standard solution. For x separately we have to prepare some concentration. We have to observe the absorbance at both the wavelength. And y component we have to prepare one concentration. Then we have to observe the absorbance of the both wavelength. And then this time we have taken mixture which consists both the sample x plus y. Okay, or tablet which consists of both the sample. Here this time we are observing the lambda 1 and lambda 2 absorbance, both the absorbance. Lambda 1 is known as a1, lambda 2 is known as a2. Here I given one graph for better understanding. I given one graph. Okay, here three graphs are there, 3 peaks are there. You see here this one, first one is this is the graph for x. Okay, this is the lambda max, this is for x. Then this one, this black one, this one is for y sample, means the standard sample y. This one is standard sample x, this one is standard sample y. And you see the middle one, that is the mixture, that may be diluted tablet solutions are tablet. You can see that consists both the wavelength. Okay, that consists 2 peaks. Here one peak and second peak. First time here we are observing the lambda max of the first component, standard solution. And second, this black one is the standard solution of y, second component. Okay, separately we are observing. Okay, and third one and mixture it is having both the components. You see here this one is considered as lambda 1, here this one is considered as lambda 2. Here this point is isobestic point, IBP, isobestic point or isoabsorptivity point. Here this point means what is the meaning of this? Here this drug, x drug and y drug. Here both the absorbance of these two. Okay, both the absorption of these two drugs are same at this wavelength. This can be considered as lambda 3. Okay, at this wavelength both the absorptions are same. Isoabsorption point or isobestic point, nothing but the wavelength at which molar absorptivity of two component is same is known as isoabsorption point or isobestic point. Okay, this is the graph. Okay, here then you come here. I told you that at lambda 1 is a1, at lambda 2 is a2. This is for dilute sample, mixture or tablet. Here at lambda 1 you consider a1 equal ax1 into bcx plus ax2 into bcy. Means ax1 we know that here this is the a1 nothing but lambda 1, right? ax1 means molar, here we can see molar absorptivity of x sample at lambda 1 first wavelength. Then b means we know that this is the path length. Here C means concentration of the x sample. Then ax2 molar absorptivity of x at second wavelength. Molar absorptivity of x at second wavelength. Then Cy means concentration of the y sample. Okay. Then A2. Then here A by 1 means if our A2 means at lambda 2 is known as A2. Okay, A2 means A by 1. This time y sample. Okay, second sample. Okay, A by 1 means you can see here. Okay, A by 1 molar absorptivity of y at y1, that is known as A by 1. Molar absorptivity of y at first wavelength. Y1 means first wavelength. Okay, B means concentration. Path length. C means concentration of y. A by 2 means molar absorptivity of y at second wavelength. Here Cy means concentration of the y. and we know that path length. And you need to remember that b is the constant that is always having 1 centimeter only path length. Here then on rearranging equation we will get these two. Okay, concentration of x, concentration of y. Here finally we have to determine the concentration of the both the drugs in the mixture in the daily sample. Here concentration of x sample we can determine by this formula. Concentration of y can be determined by using this formula. This can be obtained by rearranging this equation. You can see A2 into AY1 minus A1 into AY2, AX2 into AY1 minus AX1 into AY2. Here A2 we know that A2, here capital A2, capital A1, those are the absorption. Absorption at wavelength 1, first wavelength, absorption at wavelength 2. That is in the mixture. Okay, mixture. Okay, then here AY1 we know that absorptivity of Y sample at first wavelength. AY2 means absorptivity of Y sample at second wavelength. A1 means absorptivity at lambda 1. AX2 absorptivity of X at second wavelength means lambda 2. Then absorptivity of Y at first wavelength. Then AX1 we know that absorptivity of X at first wavelength. Then molar absorptivity of Y at second wavelength. Here two things you need to observe. We need absorbance in the text and we need absorptivity. Absorbance and as well as absorptivity. Absorbance directly showing in the graph. Okay, if you scan any compound in the UV visible spectroscopy. Here absorptivity we need to calculate. Okay, by using some values. I will tell you. Cy, this is the formula. How we can determine absorptivity. Okay, AY1 or AX1, AY2 or AX2. How we can determine absorptivity of those components? Here you can see this is the Beers-Lambert's-Law equation. Here C equal A by epsilon B. Here we know that epsilon is the molar extinction coefficient. We need molar extinction coefficient. So it will come this way, then A by Cb. You see, by using molar absorptivity can be calculated by using Beers-Lambert's-Law equation. Okay, we know that A equal to epsilon Bc or small a Bc. Here molar extinction coefficient is equal A by B into C. By using this formula, we can determine absorptivity. Simply we can determine, okay, A equal A by C, because B you consider as 1 centimeter only. Okay, then epsilon equal A by C or small a equal A by C. If you know the absorbance and concentration, we can determine the absorptivity. For better understanding purpose, I have taken experimental values. Okay, I have taken experimental value. By using simultaneous equation, we can determine mixture. We can determine the concentration present in the mixture at tablet. You see, here this one is the drug category, paracetamol and diclofenac and tablet. Okay, paracetamol supplies we have prepared a standard solution of paracetamol and diclofenac. Okay, diclofenac standard solution I have prepared. Then tablet it consists both paracetamol and as well as diclofenac. Here first the concentration. Here series of standard solution I have prepared, paracetamol and diclofenac. First here okay, here I have taken 10 microgram per ml, diclofenac 10 microgram per ml and tablet also 10 microgram. And remember the tablet consists both the drugs. Here like this one and this one. Tablet consists both the peaks, 2 peaks. Here absorption at 2. Here actually paracetamol having lambda max at 243. Diclofenac having lambda max at 276 nanometer. Okay, paracetamol having 243 in this, diclofenac having 276. Yeah, okay, by example we consider. But here we need to have for this we need to have both. We need to have absorbance at both wavelength for each drug. Okay, paracetamol we can say at 243 nanometer 0.1712, 276 nanometer 0.3246. It has given absorbance like that. Then absorptivity at 243 nanometer of paracetamol. How you can see 0.0172. That is AX1. Okay, AX1. This is the AX1. Then absorptivity of paracetamol at 276 nanometer. That is 0.03246. That is AX2 value. Then same diclofenac absorbance at 243 nanometer. This one 276 nanometer. This one. At then one absorptivity of diclofenac at 243 value this one, that is AY1, and absorptivity of 276 nanometer, this is AY2. how we will get 0.017, that is AX1 value? We know that absorbance value A by C. Formula is A by C. What is here? Consider 243 nanometer. What is the concentration of here formula? We know that A by C. Okay. What is the absorbance at 243.1 1712? Then what is the concentration? 10. So if you do like this, you will get 0.0172. Same thing. How we will get this one AX2? Here this time 276, right? What is the absorbance at 276.3246? Divided by 10. Then you will get 0.03246. Same you will get. Okay. Then come to tablet. I have prepared equivalent weight and prepared 10 microgram per ml. Then I got 0.8270. This is absorbance A1 at lambda 1. Lambda 1 is the 243 and lambda 2 is the 276. 0.8270, 0.2077, that is A2. Okay. Then what are the values required under this? So here these two are the AX1, AX2, AY1, AY2. In the sample or in the tablet in the dilute solution, these values, the absorbance values are considered as A1, capital A1 and A2. Then substitute this A1, A2 and AX1, AX2, AY1, AY2 in this formula. Okay, here CX is X is the paracetamol, Y is the diclofenac. So if you substitute all these values in those formula, you will get 1.32 mg of paracetamol and 7.65 mg of diclofenac. Okay, in the tablet. So finally, by using simultaneous equation, you will get that the tablet consists 1.32 mg of paracetamol and 7.65 mg of diclofenac found in the tablet. If you substitute these values in simultaneous equation, finally you will get this concentration. So by this way we can determine concentration of the component if two are present in the solution, if more than one present in the solution. This is about single component analysis and multi component analysis. Thank you.